Okay, so what we have here is that um, x is a function of t, y is a function of t, um, and since u, um, is a function of x and y, you can also think of that as, those are both functions of time. And so u does have a defined relationship with t. And anyways, we're going to do this problem using the product rule and the chain rule. But you have to think of x and y as functions of time. What hints are there that x and y should be thought of as functions of time? Yep. That's true, yeah. Yeah, that's what I was going to say is the dots over the x and y. You know that there's such a thing as derivatives with respect to time, so you know that those are functions of time. So, okay, let's go through. So we're looking for du dt, and by definition, that has the same meaning as u dot. And so the product rule says we're going to, so for the first component, we're going to take the derivative of the first thing times the second, plus the first thing times the derivative of the second. Okay. And, depending on what you're given to write this in terms of, you have to think about how to represent it. But the things that we're trying to use in our final answer are x, y, x dot, and y dot. So I'm just going to write this as derivative of the first times the second, plus the first times the derivative of the second. And that's it for the first component. And now we'll go to the second component. And this one, I'm going to think of it like this. I'm sort of going to break it into pieces. So we have x dot, the derivative of the first thing I'm using the product rule here. So derivative of the first thing that's multiplied together times the second thing plus the first thing times the derivative of the second thing. And I'll write that as, so the derivative of this whole thing. Okay. Well, let's just go through it systematically. We know that it's this, but this time derivative of y squared isn't one of the things that we're trying to represent this. So I'm going to just keep going now. Okay, so we still in the first component we have x dot y plus x y dot. Here we have x dot y squared, and then we have plus x times this thing. Well, what is the time derivative of this thing? Well, we can think of it as the time derivative of y squared with respect to y. I guess I'll write it out as dy squared dy times dy dt. That's what the chain rule says. And then now I can do the last step and go x dot y plus x y dot. And then for the y component, x dot y squared plus x times what's the derivative of y squared with respect to y? 2y. And so I'll write this as, I'll pull the 2 out to the front. So we have 2x y dy dt is y dot. And so there's the final answer. Any questions about that? So product rule and chain rule together. Any other homework questions? Okay, so we're doing particle kinematics. And there were 4 topics that I said we're going to deal with in particle kinematics. Later, we're going to revisit particle kinematics in a rotating coordinate system. This is in a non-rotating coordinate system. And the first of these topics was that the acceleration is the time derivative of the velocity and the second time derivative of the position. The second topic was the chain rule. So this was in a kinematics context. This is where we're saying A, the acceleration as a function of a position variable. I'm just going to call it S. That could be X, Y, or Z, or it could be some more complicated thing, but it's always a position variable, is equal to the derivative of the velocity with respect to the position variable times the position variable derivative with respect to time. Then the third thing is relative motion. And the fourth thing is circular and spherical motion. You can think of these as they're like the same thing, but one's in 2D and one's in full 3D. And we have so far talked about this, and these two are left. And we're going to see throughout these class that we're going to use these two together a lot. So think of these two as sort of natural partners with each other. Okay, so the first thing we're going to talk about is relative motion. And I would say that the most important use for this in dynamics is for finding the true acceleration. Let's say I'll call it the acceleration vector. When given the acceleration measured by an accelerating coordinate system. Okay? So why is that such an important thing in dynamics? Well, remember that all of our classical kinetics equations, all of Newton's laws and things you can derive from Newton's laws, depend on an inertial coordinate system, which means the coordinate system is not accelerating and the coordinate axes are not changing orientation. Okay? Changing orientation is going to be a little more complicated, and that'll come up later in the class. But this is the first half of that. So what do you do if you want to use Newton's laws, but your accelerations are measured by an accelerating origin, an accelerating coordinate system? This is how you do it. Okay, this is how you do it. That's what that song is about. I mean, I haven't listened to the rest of the lyrics, but I assume. So as we do this, remember these things. So first, think of a coordinate system as a video camera measuring motion. Remember that there are, this is what I just said, two ways for a coordinate system to be non-inertial. The first way is the origin accelerating. And the second way is for the axes, the coordinate system axes, to be changing orientation. And relative motion is how you deal with this one. And since now I have like MTV songs in my head, I want to just take a second and show you an example of, so think of this as like your example of how a coordinate system is a video camera, and how accelerating coordinate systems mess up the way physics equations work. Okay, and it's also a nice song. Actually, I'm gonna turn this.
You have some like method of relative motion in his theories, right? So with that,
With what?
like Galilean or something?
Oh yeah, yeah. I guess they do call it Galilean relativity that we're going to be talking about. Although Galileo, as opposed to Einstein's relativity, which is very different, we'd rather not think about that. But Einstein's relativity only comes into things when things are going really, really fast, like some significant fraction of the speed of light. And so in this class, we're just not worried about that. Nothing in our everyday experience, Mach 10 fighter jets or anything, is any significant fraction of the speed of light, you know. Okay, and then the third thing, and this is for the whole class. So in this class, keep this in mind. Any two coordinate systems in a problem are instantaneously aligned. Okay, well, right now, we're not talking about coordinate systems that are rotating. So the coordinate systems, if you have two different coordinate systems in a problem, this is to me, so this is to you, two coordinate systems, they're gonna, whatever they're doing, they're gonna maintain the same orientation as they move around. Okay, so if they weren't aligned, if they were like this and moving around, but neither one was rotating, people in my statics class, how would you deal with that mathematically? It's really pretty simple. We're just not going to spend time doing it. Exactly. You'd use rotation matrices, and that's all you need to do. It's a bigger problem if you have one doing this and one doing this. Okay, that's a rotating coordinate system. But even in that case, when we do rotating coordinate systems later on, we're going to always be taking a snapshot at the instant that they come into alignment. Okay, so, and again, you would deal with that with a rotation matrix. It's not hard. We're just not going to do it. But so that's why I say instantaneously aligned. If you wait till the next second with rotating coordinate systems, they'd be out of alignment. But for us, they'll be in alignment. Okay. And in order to introduce relative motion, the easiest way, the most intuitive way, is to first think about relative motion for positions. Once we have relative motion equations for positions, we're just going to take time derivatives of everything to get velocity and acceleration. So, okay, let's say that we have coordinate systems, video cameras, at two locations. So this is location A, this is location B, and both of those two video cameras are observing something that we'll label C. Okay, this is the ball we're doing calculations for or whatever. But we'll think of that as a coordinate system, that as a coordinate system. And I'm going to, when you introduce any new math, you usually have to introduce new notation, unfortunately. So here's the notation I'm going to use for this. So this vector here is the position of that C as observed by coordinate system A. Okay? And I'm going to, the notation I'm going to introduce, this is the notation everybody uses for this, is the position of C relative to A. Relative to means as observed by. Okay? And then this vector is the position of C relative to B, as observed by B. And then I'm going to define one more thing to complete this triangle. That is the position of B relative to A.
So you said position of C relative to A is what A sees.
What B sees. So these are both valid coordinate systems. Okay? You can take measurements in either one of these. P of C relative to A is where coordinate system A sees, the measurements of C as measured by coordinate system A. Position of C relative to B is how the coordinate system at B measures the location of C. And you got to memorize this subscript meaning until it's just built in. It'll pay off. So here's the subscript meaning. Subscripts A over B means A relative to B. Okay, or in other words, A as measured by B. Okay?
Can I, so P sub A over B is the location of the A origin in B's coordinate system.
Which one? So,
I'm
Po-
a little confused.
yeah. Okay. So, so each one of these, the first subscript is the object you're looking at, and the second subscript is the coordinate system that's looking at it. Okay. So this is the position of C relative to A. This is the position of C relative to B. This is the position of B relative to A. Okay, so this one right here. Okay, so look at that vector. That is the video camera at A locating C, and that is called the position of C relative to A. Okay, so chant along with me. The position of C relative to A. 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 The position of C. This is most of what the protest at downtown was. We were mostly doing relative motion.
Another way to think of it, like tip and tail, the tip is going to C.
Don't think of it that way. Think of it the way I tell you to think of it.
I have a question. So for the C and B connection, why is it also not relative to A?
The C and B connection. Okay, because that vector that I drew it's only the measurement that's taken by that video camera at B.
Okay.
Okay, so what those are, each one of those is a vector. You know, you could think like with the alignment of the coordinate system that I drew here, you could estimate what these components are. You know, maybe this is basically straight 50, 0, say, you know, depending on what the distance is. This one is maybe 43, 50, something like that. Are you with me on the, like, where I'm coming up with these components? Well, this one is 30, negative 25, whatever. Okay. And what those vectors mean is that is the distance and direction measured by, you know, that specific video camera where that vector is starting. Yep.
So is the video camera the origin?
Yes, the video camera is the origin, correct.
And what is the relationship between the P position of C relative to A and P position of A relative
Yes.
to C?
Right. That is what so first we need these definitions, and then the key thing is that relationship, exactly. And so that relationship is this. For any 3 letters, this works. For any object and 2 coordinate system origins. So the position of C relative to A is equal to the position of C relative to B plus the position of B relative to A. And here's how you identify. So here's the memory device for this. Here's how to check whether you have them in the right order. Memory. Think of matrix multiplication of those subscripts. Not matrix, sorry, fraction. So fraction multiplication of subscripts. And that equation has to hold, or you have them in the wrong order. Okay, so like look at what I have here. Mine says that C over A is equal to C over B times B over A. And that works, okay? If you put them in any other order, it wouldn't work. Okay, so like if you put it as, try position of C over B is equal to position of C relative to A plus position of B relative to A. If you write it out as a fraction multiplication, it's wrong. So that's the wrong order.
What if C is also a video camera?
Yeah, really, they're all video cameras.
So that's-
Everything's video cameras. And so,
And then what if one video camera is measuring in metric and one is measuring in imperial? Like one's measuring in inches.
yeah, well, we're not going to worry about that. I mean, you always have to put everything in matching units before you do any calculations. Yes.
So, for comparing this to static, when we did the bunch of joins, and we always used the lowest
Yeah.
upper join to calculate
Right.
them. Is this the same?
No, it's not. It's just similar looking notation.
Okay.
They don't have any relationship. Yeah. That kind of stuff, it gets so confusing, but okay. And what about velocity and acceleration? So this is the equation. So that we're going to start with, and then take time derivatives of that equation. And what you get is the velocity of C relative to A is equal to the velocity of C relative to B plus the velocity of B relative to A. So that's the velocity relative motion equation, and it looks just the same. And then the acceleration relative motion equation, acceleration of C relative to A is equal to the acceleration of C relative to B plus the acceleration of B relative to A. And all of these, you have them right if the fraction multiplication works. Yes?
What are B and A derivatives of this up? So does it matter if B is a derivative of position or time?
Yeah. I mean, they follow the derivative definitions of acceleration. So take the first time derivative of that position relative motion equation gives you the velocity equation. You're just taking time derivatives of both sides, and this is what you get. Take another time derivative, and you get the acceleration.
I was just thinking of the example of the chain rule where you want acceleration with respect to time, but you have velocity with respect to position. And
Yeah, I mean, this is all, we have all these
that
things.
apply here?
No, that's different.
Would be the most together.
Let's just keep going through this, okay, for now, and then I'll take questions at the end. But it's going to make more sense once we do some examples and stuff. One thing that can be helpful sometimes is, so we talked about the fact that really everything, including, so say you're tracking the motion of a bird at sea, okay? Well, that bird, we're going to imagine that really having a coordinate system on it too. And just like you're videotaping this bird is videotaping you, okay? And so what's the relationship between your video and the bird's video? And they're opposite. That's exactly right. And so notice that sometimes it's useful sometimes handy to recognize that the position of, I'm just using random references, but the position of M relative to N is -1 times the vector position of n relative to m. And that's true with velocity. So the velocity of m relative to n is negative velocity of n relative to m. Excuse me. And same with acceleration. So acceleration of m relative to n is negative acceleration of n relative to m. Okay, so let's start to see some examples. Now, I started with that position relative relative motion equation, and then we derived the velocity one and the acceleration one. But remember that the acceleration one is going to be the most important one in dynamics. And that's because this is the one we use to correct for non-inertial coordinate systems. Okay, so let me do an example with acceleration to start with. I think actually I have a couple with acceleration. So let's say you have an elevator, and just as it starts to move, the passenger drops their keys. According to a camera mounted to the elevator, the observed acceleration of the keys is 11.5 meters per second squared down. So first, what's the acceleration of the elevator? And is the accelerator, no, there's no accelerator. Is the elevator accelerating up or down? Okay, well, if you tried to do Newton's second law based on that 11.5 meters per second squared down, Newton's law would not appear to hold because the camera mounted to the elevator is a non-inertial coordinate system. Okay, so if you want to use Newton's laws, you need to correct for that. We're sort of asking a different question here. We're asking something about the acceleration of the elevator. So, okay, what we want is, let's say that I'm going to say E is the coordinate system mounted to the elevator. K is the keys. And I'll call G the ground. So you can imagine this is like a glass elevator and there's a camera outside that's watching what's happening, through the glass.
Could it be mounted on like the bottom of the elevator, like?
Yeah, the bottom of the elevator shaft. Yes.
But the camera is moving, right?
The camera is moving, correct. So this is fixed to the ground. Okay, so let's put these three things. You really can put them in any. So one way to go is you can put these subscripts in any order you want, and then just use the negative relationship to adjust them until the fraction multiplication works. Okay, that's one way you can do it. I'm going to do it like this. I mean, this is a pretty common way, is that you have an object you're observing and two things observing it. And so I'm going to do it as the acceleration of the keys relative to the ground is equal to the acceleration of the keys relative to the elevator plus the acceleration of the elevator relative to the ground. You can see if you do the fraction multiplication with those subscripts, the e's cancel and this works. So you know that it's, check the fraction multiplication and then you're right if it works. Okay. And now let's start putting this stuff in. So do we know anything about the acceleration of the keys relative to the ground? Yeah, that's free fall. So we know that's 0, negative 9.81. Do we know the acceleration of the keys relative to the elevator? Yep, that's what we're given. So that's 0, negative 11.5. And then we have this. And so now you can subtract the vector on the right side of the equation from the left side, and you get that the acceleration of the elevator relative to the ground is 0, negative 9.81 minus 0, negative 11.5. And so that is 0, positive 1.69. Okay, so that is the first answer. That is our vector acceleration of the elevator. And now the second one says, is it accelerating up or down?
It's positive, so it would be going up.
Positive, so up, yeah. I mean, that's, I didn't tell you what my coordinate system is, but it's a pretty common coordinate system, Yeah. This is the vector, this is the acceleration of the elevator relative to the ground. Okay, so this is that camera that's mounted to the ground, mounted to the elevator shaft floor, or looking at this glass elevator from outside. That camera can measure how much the elevator is accelerating, and that's what it sees. And so this is accelerating up. Okay, so let's go into let's think about these answers a little bit. So is an elevator always accelerating when it's moving? No, it accelerates to get up to speed, then goes like a constant speed for a while, and then accelerates to stop. Okay, so this is only at the start or end of the motion of the elevator that you would have a result like this. Do we know whether the elevator is moving up or down? Do we know anything about the velocity of the elevator?
No,
We don't. This could be at the start of the motion when it's moving up, or it could be at the end of the motion when it's moving down. Well, actually, so I guess we do know, because I think it says it starts to move.
Yeah.
But that could equally, this upward acceleration could equally be the thing speeding up, going up, or slowing down, moving down. Yep.
So when it slows down to stop, it's still moving up?
When it slows, okay, so when you have any one-dimensional motion, if the acceleration and the velocity are in the same direction, the thing is speeding up. And if they're in opposite directions, it's slowing down. So, so like if this elevator is moving up and the acceleration is up, then that's during the period where it's speeding up. If the elevator's velocity is down and the acceleration is up, then that means it's slowing down. So that has to be at the end of the motion. Yeah.
For this to work, you need your point of reference and two other.
Yeah. You always need, yes, you always need three. I mean, I think probably just think of it always as three origins that are moving around. One of them is usually the ground. One of them is usually some object, you know, but really think of them as three equal coordinate systems. But if one is the ground and one is a bird or a ball or keys or something, you can always say it'll always work with that fraction multiplication rule to have the acceleration of the object relative to the ground is equal to is equal to the acceleration of the object relative to the intermediate, like say a vehicle of some kind, you know, plus the acceleration of the vehicle relative to the object, you know. So very often, I'm going to put this in parentheses, very often you can think the acceleration of the object relative to the ground is equal to the acceleration of the object relative to the vehicle plus the acceleration of the vehicle relative to the ground. Okay, so in any problem where you have an object and you have a ground and you have a vehicle, you can do it in this order and it'll work. You know, you can look at that and it works with the fraction multiplication. Okay, let's do one with velocity. Oh, no. Yeah, let's do one with velocity first. Okay, so let's say you have a big train car. And a person running on the train. I'm going to have my x-axis this way and my y-axis this way. And a camera on the ground says the train's velocity is 30 meters per second. And the man's velocity is 35.0. So first, what's the man's velocity?
Is that the velocity, so the main velocity relative to the train and the train's velocity relative to the ground?
Yeah, so think of this. Let me reword this actually. So, like how fast is the man running? Is he breaking the world record for the 100-yard dash or whatever? They don't keep that anymore. How fast is the man running? Yeah, that's right. but don't give it away. And then,
Which way is the train moving? Oh, so positive, so it's going in the right direction.
correct. Yep. And then second is the man running left or right. Okay, so in this example, can we use is there an object and a vehicle and a ground? Yeah, so I'm going to say G is ground, T is train, M is man. And I'm going to write this as the acceleration of the man relative to the ground is equal to the acceleration of the man relative to the train plus the acceleration of the train relative to the ground. And you can see fraction multiplication works with that. So this is a valid relative motion equation. And we're doing velocity, not acceleration. So change these all to V's.
If you don't specify what the velocity is relative to, what should we assume? Is it
Yeah, well, I mean, if we're trying to figure out how fast a person is running, then that's going to be relative to the thing that their feet are touching. Okay.
I was just confused by
Yeah.
the way the questions were.
Yeah. So what that's saying is how fast is the man's running? That's going to be the velocity of the man relative to the train.
Okay. The velocity of the man given is the velocity of the man relative to the ground?
Ground. Yep. Because that video camera is mounted to the ground. Okay. Okay, so man relative to the ground is 35.0. And that's equal to velocity of the man relative to the train. We're not given that. Plus the velocity of the train relative to the ground. That's 30.0. And so the velocity of the man relative to the train is equal to 35.0 minus 30.0. And so you get 5.0 meters per second. So the speed of the man is the magnitude of that. So like the run speed is just 5 meters per second, which is not close to the world record. It's like maybe 11 miles an hour. Anyone know how fast the world record top human speed is?
Like 30?
Yeah, about 30. Yeah. A shade under, yeah.
Or,
In miles per hour.
Feels so slow in your car though.
Yeah. And then the direction, which direction, left or right? Right, because of the sign of that vector.
So this here is the one that the train is seeing that the man is running. Right?
Yeah, the speed is, so you'll see these a lot of times in physics problems where like with swimmers or runners or whatever, the speed that the thing is sort of like how fast is the thing going is always referring to compared to whatever medium it's in, you know? So like if a person is on a fast wave swimming, you know, how fast that person is able to swim doesn't have anything to do with the wave speed. It's how they're swimming relative to that wave. And it's the same with running. Like if you're on Well, think of a treadmill, like the speed that the gym wall measures when you're on a treadmill, no matter how fast you're running, it thinks you're going 0, But the speed you're really running is the speed is your speed relative to, your 0 miles per hour relative to how fast the track is going. Yeah. Okay, let's do one more. This is a lot like the last one, but so let's say a car is in an accident. And a camera mounted to the car sees, say a coffee cup falls off the console when this collision happens. And this camera mounted to the car sees the coffee accelerate at 15, negative 9.81. So first, what's the acceleration of the car? And I'm going to show you the direction the car is going. Okay, so here's the car and its relationship to the coordinate system before the collision. And does the collision happen at the front or the back of the car? Okay, so in this one, is there a ground and an object and a vehicle? Yep, so I'm going to just use that order. So I'll call it G for ground, C for coffee. Oh no, now I've painted myself into a corner here. I guess I'll use V for vehicle. And I'm going to do it as the acceleration of the object relative to the ground is equal to the acceleration of the object relative to the vehicle plus the acceleration of the vehicle relative to the ground.
Your wife, they copies your object.
Yeah. Oh, why is it?
Yeah.
Oh, well, so usually the way these problems are going to happen is there's going to be like two kind of environments that have cameras mounted to them. And then usually the object, there's not really, I mean, you can always imagine that it has a coordinate system attached to it, but usually in the wording of the problem, it'll be something that both of those other two environments are observing. Okay. But we could do this in another, let's do it in another order after this and think about how you would go about doing that. So, okay. Acceleration of the car relative to the ground. That's the thing that we're trying to find. So we don't know that. The acceleration, no, that's not because of my subscripts. Yeah. Okay, so C is coffee. So acceleration of the coffee relative to the ground is given. So that's 15 negative 9.81.
That's, the one, you said 15 negative 9.81 is the car seeing the coffee, though, not the ground seeing it.
God dang it. Right. Okay, what do we know about the acceleration that the ground would see for something that's in free fall? Yeah, that's 0, negative 9.81. Acceleration of the coffee relative to the vehicle, that's the one that's 15, yeah, negative 9.81. And then the acceleration of the vehicle relative to the ground is what we're trying to figure out. So I'll just leave that as a variable. And so the acceleration of the vehicle relative to the ground is equal to 0, negative 9.81 minus 15, negative 9.81. And that is negative 15, 0. Okay, so this thing is accelerating in the negative x direction. So did the collision happen in the front or the back? Yep. And you may unfortunately know this from experience or whatever, like if you have a sudden acceleration forward in the car, everything in the cab goes backwards. Anything that's sitting tips over backwards or whatever. If you have a sudden acceleration backwards, everything in your vantage point accelerates forwards. Okay. Like when when people are injured in collisions, it's a sudden acceleration backwards, like a collision with the front of the car that makes people hit the windshield or the steering wheel or hit their legs on the front of the car, that kind of stuff. Okay. Could we have done this any other way? We could have said that the thing we're trying to find is the acceleration of the vehicle relative to the ground. And then we could have put in the things that were given. Okay, so we could have said acceleration of the vehicle relative to the ground, which is what we want, is equal to, so what things are we given here? We're given the acceleration of the coffee relative to the ground. And we're given the acceleration of the coffee relative to the vehicle. Yeah, and so now we can go and use these things. Wherever I put them, sometimes handy things. You can switch the subscripts if you switch the signs. So we can replace this with negative acceleration of v over c. Now it works. My notation there is weird, but so now we can say the acceleration of the vehicle relative to the ground is equal to 0, negative 9.81 minus 15, negative 9.81 is equal to negative 15, 0. And it works just the same. Any questions about that?
Explain again, part B, the collision.
Yeah, so then you would answer that the same way. So the collision was in the front of the car, you know, and you can see that here from the fact that it's an acceleration in the negative direction. These collisions, you know, a collision never pulls on things, it only pushes. So in order to have an acceleration in the negative x direction, you have to have something pushing on the front.
Okay.
Okay, so now here's where we are. So particle kinematics in non-rotating coordinate systems. We have the derivative relationships that says acceleration is equal to v dot is equal to p double dot. We have the chain rule that says the acceleration vector as a function of a position variable is the derivative of the velocity with respect to the position variable times the position variable with respect to time. We have relative motion. And then fourth, we have circular and spherical motion. Okay, and now we've done these three, and we'll be on the last one next time. Okay, let's do the